Step outside on a clear night and look up. The sky is dark, most of it anyway. There are stars, brilliant, scattered, but between them, emptiness, deep, total, unbroken black. That darkness feels natural, obvious, inevitable. It is none of those things. In 1576, an English astronomer named Thomas Digges published a map of the universe in which the stars extended outward in every direction, infinite in number, infinite in space. If Digges was right, if the universe truly contains infinite stars distributed across infinite space, then the mathematics are absolute and unforgiving. No matter which direction you look into the sky, your line of sight must eventually terminate at the surface of a star. Not probably, not likely, must. Every single ray of your vision, extended far enough, would hit burning stellar plasma. The night sky should not be dark. It should be a solid, blinding, unbroken dome of fire, every square degree blazing at the surface temperature of a star. The fact that you can look up right now and see black space between the stars is one of the most important clues the universe has ever handed to science. This problem has a name. Astronomers call it Olbers Paradox, after the German astronomer Heinrich Wilhelm Olbers, who published a formal description of it in 1826. But the paradox is older than Olbers. It begins with the most fundamental question in cosmology. Is the universe finite or infinite? For most of human history, the universe was assumed to be small and bounded, a crystal sphere of fixed stars surrounding a central Earth. That changed in 1576, when Thomas Digges became the first European astronomer to publicly propose a universe in which the stars extended outward without limit. Digges drew his infinite stars on the page and noted they extended beyond any border he could draw. He believed the universe had no edge. But he also noticed, and quietly worried about, a consequence he couldn't resolve. If the stars go on forever, why is the sky not as bright as the surface of the sun? Johannes Kepler raised the same question in 1610 and drew the opposite conclusion. Kepler argued that the darkness of the night sky was definitive proof the universe is finite, that the stars do not go on forever, and there is therefore not enough starlight to fill the sky. His reasoning was sound. His explanation of why was not yet complete. For the next 2 centuries, the paradox simmered without resolution. In 1744, the Swiss astronomer Jean-Philippe Loy de Chezeaux calculated that an infinite, eternal universe filled with stars would produce a sky as bright as the surface of a star in every direction. He suggested, with little conviction, that interstellar matter might absorb the excess light. Olbers made the same calculation in 1826 and proposed the same solution. But the absorption argument fails immediately under scrutiny. If space were filled with absorbing dust or gas, that material would eventually heat up from the absorbed starlight and re-radiate the same energy. The sky would still blaze. The problem could not be solved by placing anything between us and the stars. In 1848, the American writer Edgar Allan Poe, not a scientist, but a visionary of extraordinary intuition, published a prose poem called Eureka. In it, Poe proposed that the darkness of the night sky was not a failure of starlight, but a failure of time. He wrote that the only way to explain the voids in the sky is by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us. Poe was correct. He solved Olbers' paradox 40 years before the professional astronomers did, in a poem, using nothing but intuition. The formal mathematical treatment came in 1901 from Lord Kelvin, the British physicist who had also calculated the age of the Earth from cooling rates. Kelvin showed rigorously that in a finite-aged universe, only a finite shell of stars would be visible, only those close enough for their light to have reached us in the available time. The sky is dark because the universe is not old enough for starlight from the far reaches to have arrived. But this raised a deeper question. Why is the universe not old enough? Why does time have a beginning? To answer that, science needed a revolution. In 1905, Albert Einstein published his special theory of relativity, and in 1915, his general theory, a complete reimagining of gravity, not as a force, but as the curvature of space-time itself. Einstein's equations described a dynamic universe, one that could expand, contract, or curve, not the static, eternal cosmos Newton had imagined. Einstein himself was uncomfortable with this implication and added a term to his equations, the cosmological constant, specifically to hold the universe static. He later called this the greatest blunder of his life. In 1922, the Russian mathematician Alexander Friedmann solved Einstein's field equations without the fudge factor and showed the universe must be either expanding or contracting. In 1927, the Belgian priest and physicist Georges Lemaitre independently reached the same conclusion and went further. Lemaitre proposed that if the universe is expanding today, then running time backward, everything must have once been compressed into a single, impossibly dense point. He called it the primeval atom. We now call it the Big Bang. In 1929, the American astronomer Edwin Hubble published the data that confirmed Lemaitre's prediction. Hubble had been studying distant galaxies at the Mount Wilson Observatory in California using a 100-inch telescope, the largest in the world at that time. He measured the light spectra of 46 galaxies and found something extraordinary. The light from virtually all of them was shifted toward the red end of the spectrum, not randomly, not by chance, systematically, with a clear pattern. The further away a galaxy was, the more its light was redshifted. This is the Doppler effect applied to light. When a source moves away from you, its waves are stretched, pushing the light toward longer, redder wavelengths. Every galaxy Hubble measured was receding, not from a central point, not from Earth, but from every other point simultaneously, because space itself was expanding. The universe was not static, it was getting bigger. And if it is getting bigger now, it was smaller before, and smaller still before that. And at some definable, calculable moment in the past, everything that now exists was compressed into a state of unimaginable density and temperature. That moment is now calculated to have been approximately 13.8 billion years ago. This is the age of the universe, and it is finite. This is the first part of the answer to Olbers Paradox. The universe has an age, and that age is not infinite. Light travels at 299,792 kilometers per second, the fastest anything can move in the known universe. In 13.8 billion years, light can travel a maximum of 13.8 billion light-years. That defines the edge of what is called the observable universe, the spherical region of space from which light has had enough time to reach us. Stars and galaxies beyond that boundary almost certainly exist. But their light has not arrived yet. We cannot see them. They do not illuminate our sky. That is why the sky is dark. But there is a second part of the answer, and it is even stranger. The universe is not only finite in age, it is also expanding at an accelerating rate. Space itself is stretching, and that stretching carries galaxies away from us faster and faster. Some galaxies are now receding from us faster than the speed of light. Not because they are moving through space faster than light, that is impossible under relativity, but because space itself is expanding between us and them. This means there is a class of galaxies that we once could see, galaxies whose light reached us in the past, that we will never be able to see again. They have crossed what cosmologists call the cosmic event horizon, the boundary beyond which the expansion of space permanently outpaces the travel of light. The observable universe is therefore shrinking. In billions of years, the night sky will be even darker, as galaxy after galaxy crosses that horizon and vanishes, forever from view. But there is more to the darkness than the edge of time and the expansion of space. The earliest light in the universe is not visible to the human eye at all, and this is perhaps the strangest piece of the puzzle. After the Big Bang, the universe spent its first 380,000 years as an opaque plasma, a dense fog of charged particles so hot that photons could not travel more than a short distance before being absorbed and re-emitted. The universe was filled with light, but that light was trapped, bouncing endlessly through the plasma, going nowhere. Then, 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms. This moment is called recombination. The instant recombination happened, the fog cleared. For the first time in cosmic history, photons could travel freely. That ancient light, the first light ever to travel unimpeded through the universe, is still traveling today. It left the primordial fog 13.8 billion years ago and has been traveling toward you ever since. It is arriving right now, from every direction simultaneously. But you cannot see it. In the 13.8 billion years since it was emitted, the expansion of the universe has stretched those photons to much longer wavelengths. What began as infrared radiation has been redshifted all the way down to microwave frequencies. This is called the cosmic microwave background, the CMB. It was discovered in 1965 by two radio engineers at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson. They were trying to calibrate a large microwave antenna and kept detecting a persistent, uniform hiss coming from every direction in the sky, a noise that wouldn't go away no matter what they adjusted. They blamed pigeons nesting in the antenna horn. They removed the pigeons. The noise remained. A colleague put them in contact with Robert Dicke at Princeton University, who had been actively searching for exactly this signal. What Penzias and Wilson had found, by accident, while trying to remove noise, was the afterglow of the Big Bang itself. The CMB fills the entire sky at a temperature of 2.725 Kelvin, just 2.725 degrees above absolute zero. It is uniform to 1 part in 100,000. Tiny fluctuations in that uniformity, hot spots and cold spots a fraction of a degree different, are the seeds of every galaxy, star, planet, and living thing that has since formed. When you look at a dark patch of the night sky between the stars, you are looking at the CMB. You are looking at the echo of the moment the universe became transparent. You are looking at the wall of fire from 380,000 years after the beginning of time, redshifted beyond what your optic nerve can register. The darkness is not absence. The darkness is the oldest light in existence, stretched until it became invisible. There is one more layer to this story, and it concerns what lies beyond the observable universe, beyond the cosmic horizon. We do not know what is out there. We cannot know. No information from beyond the horizon can ever reach us, because light from there cannot cross the expanding space between us in any finite time. The observable universe is not a physical boundary. There is no wall, no edge, no sign marking where it ends. It is an informational horizon, defined entirely by the finite speed of light and the finite age of the universe. Beyond it, the universe almost certainly continues. Current cosmological models, particularly inflationary cosmology, suggest the universe extends far beyond what we can observe, perhaps infinitely. The inflationary period, a brief moment of exponential expansion in the first tiny fraction of a second after the Big Bang, would have stretched the universe to scales so vast that the observable portion is a vanishingly small fraction of the whole. Some cosmologists calculate that the full universe may be at least 10 to the power of 23 times larger than the observable portion. That is 100 trillion billion times larger than everything we have ever seen or measured. And yet from inside that unimaginable immensity, what you see is a dark sky. Because the light hasn't come yet. Because the universe hasn't existed long enough. Because time itself has a beginning, and you are close enough to that beginning to see its shadow. In 1998, 2 independent teams of astronomers, Saul Perlmutter's Supernova Cosmology Project and Brian Schmidt's High Z Supernova Search Team, made a discovery that shattered all expectations. They were studying distant supernovae to measure how fast the expansion of the universe was slowing down. They expected to find the expansion decelerating, pulled back by gravity. Instead, they found it accelerating. Something is driving the galaxies apart faster and faster, a mysterious energy built into the fabric of space itself, which physicists named dark energy. Dark energy currently accounts for approximately 68% of the total energy content of the universe. Dark matter, another unknown, accounts for approximately 27%. Everything you have ever seen, touched, measured, or thought about, every atom, every planet, every galaxy, and every catalog, constitutes approximately 5% of what exists. You are looking at a sky made almost entirely of things for which you have no name and no instrument that can detect them. And in that sky, the darkness is not the absence of information. It is information. It is the most precise measurement in all of cosmology, the age of the universe, written in the gap between the stars. Step outside tonight and look up again. You are not looking at empty space. You are looking at a time horizon. Every dark patch is the edge of what the universe has had time to produce. Every dark patch is the cosmic microwave background, the echo of the Big Bang, arriving as invisible microwave radiation, redshifted beyond the range of your eyes. The universe is not dark because it is empty. It is dark because it is young. You exist close enough to the beginning of everything that the far reaches of creation haven't had time to light you up yet. That thought is almost impossible to hold. You are not in the middle of an eternal, infinite, unchanging cosmos. You are standing near the beginning of something. The Big Bang was not long ago in cosmic terms, not long ago at all. The universe is 13.8 billion years old, and the dimmest red dwarf stars will burn for 10 trillion years. We are, cosmically speaking, early. The darkness above you is not absence. It is a promise, light en route, from stars we have not yet had time to see. The night sky is not proof of the universe's emptiness. It is proof that the universe began, and that you are alive, and aware, and looking, at precisely the moment when the darkness is still here to be wondered